you are dealing with a pair or how to say a set of numbers, not just single number or two or pair, right? Yeah, you are dealing with a pair of sets. Okay. Yeah. So that's why you when you start this part, you have to still you can follow the 4 rules for numbers, but in the meantime, you have to get familiar with this this new rule for the 4 rules.
Yeah. Yeah.
For example, if you want to just go to the basic, right? You to basics. Do you remember how to do the sum?
Sum.
A, B, C, D. Do you know how to do the sum? Can you say? Can you say just this 2 1 2 1 3 3 0? Can you do that sum? Can you do the sum?
Yeah. Was it?
So you got basically answer me. Do we still get square matrix or not?
Square, as in like
Do we still have?
Yeah, I'm pretty sure you still get a.
Yeah, it is. Yeah, if you because
this
2 by 2. 2 by 2, you get 2 by 2. So your job is just to finish this. What are you shifting something?
No.
Okay. Little bit. Can we just go to the whiteboard? It's not very effective. Just you just ask question. We can talk about everything about matrix from basic idea. And so if you study matrix, so there's matrix.
Yeah.
So basically it's just a set of numbers. They can both in many cases we're dealing with matrix in a square bracket. Yeah. So basically, for example, the general matrix can be written as this one. And because A11, A11, so A22, and this A12. Sorry, you have to go back to that notation. So it's A12 and until A1n. Okay. And is A. Do you remember this A21? Okay.
Oh yeah.
A22. This is A2n. A2n. If you have studied, if you have studied the proof, you have studied binomial theorem, you should be able to learn these ones. This n to n. Okay. So basically, eventually, you got because this is a square. So this is n1. Yes, that is n2.
Then n.
Get n.
Yeah.
So that is n. This is dimension of n to n. Okay, that's n to n matrix. Okay.
N by n matrix. Yep.
Yeah. Of course, we wouldn't start that. This general form. So in special case, how about a equal to a? This is just 2 by 2. Then how about say this is a1, a1, a2, a3, a4. You can use different notation. Okay.
Yeah.
And another is a B matrix. So this is just so A and B represent a matrix, not just number. This represent a lot of number. In this case, 4.
Yeah.
B1, B2, B3, B4. Okay. Now to make it more consistent notation, can we just rewrite this one? It takes some time because I think we have done all this before. Now just to have to warm up, okay? So can we just write A11, A12, A21? Yeah, that's be easier to remember. A22.
A22. Yeah.
And the B is B11, B12, B21.
Yeah.
B21 and B22. Can you see?
Yeah.
Now, can you just try? Can you remember how about the first thing is the sum? How to make the sum? How to find the sum? So what is A plus B? Can you work it out that by yourself?
Yeah. So it's A11 plus.
Mm-hmm. Yeah.
And then B. Oh,
Yeah.
oh, sorry. Yeah.
Yeah. Yeah. So this is sum. The difference is also apply for difference. So now as you do this, change the
Yeah.
sign to the minus. You see, we're still doing the sum and the difference. Do you agree? We'll do the sum
Yeah.
and difference. The only thing different is that we have to deal with many pairs. In this case, we have dealing with 4 pairs.
4 pairs. Yeah.
So somehow it is just this is just you know, it is more compact 4 rows dealing with
Yeah.
numbers. Okay, but of course things can get a little bit complicated if you just can we just go to the go to multiplication. So can we just the sum and difference and the difference.
Yeah.
So in this way, we will review these basic ideas in matrix.
Yeah. Yeah.
So basically, in this case, can we second we just talk about the product or multiplication? A product, can you product?
Yep.
So basically, how to do say A times B. So
Yeah.
do you
Let me
remember?
just.
Yeah, do you remember?
Yeah, I remember like it's so it'd be I remember there's a rule like not rule but it's like columns and rows. So it's like
it is a row because all you learn is just the algorithm. It is a row. Matrix is a row. Matrix is a
yeah.
row.
B11 plus A12 B21 then it's good.
So A11, B11,
Yeah.
yes.
And then A12 B21.
Yeah. That's
And
right.
a bit out of space if I were to draw.
Yeah.
A12 times B12 plus A12 times B22.
Yeah, that's right. True. That's right.
Yeah. Oops. That's
yeah. So basically, it's follow this rule. If you use this, if you use this row here, and you pick up the column, you pick up column this one. So that's just give you indicator how to do that.
Yeah. Oh, I made a mistake here.
It's all right. You still can remember that. That's good. So
yeah.
You know that. Then we come to your first question. What is a unit matrix? What can we do with unit matrix? Okay.
Unit matrix.
Yeah.
That's the 1, 0, and then 0, 1.
Yeah. We just try unit, right? Unit matrix.
Yeah.
You want to try, for example, how about say the 2, 1, 4, -1 times say unit 1, 1, 0, 0. Do you want to try this?
Yeah. So it's whoops. So it's 2 times 1 plus 4, which is 6. Oh.
2 times 1, 4 times 0 is 6.
Oh, no, that's my bad. 2.
Yeah.
And then the next one is A1. 4 times 0 plus. Oh, never mind.
Are you looking for this one or which cell?
Oh no, I was just doing the one below that.
Yeah, below that is easier.
Yeah, so 1 times 1 plus 1 times 0, which is where? 1 times 1.
-1 times 0.
Yeah. Yeah, so it's just 1.
Yeah.
Because it's 1. And then this one is just... Then it's A4.
Yeah.
Yeah. 4 times 0. And then 4 times 1, which is just 1. And then
4 times 0 plus 4 times 1. Be careful.
yeah. Oh.
4 times
4,
1 plus 4 times 0,
yeah.
1.
Yeah.
Yeah.
Oh, that's my bad.
It's okay.
Oh, does it? No. -1, and then it equals the same thing.
Yeah. What is your conclusion? Yeah.
When you multiply by a unit matrix, it equals the same thing. So
Yeah.
like.
Yeah, that's very good. That's conclusion.
Oh, is that why it's called a unit matrix?
That's right.
Because
so for example, if you have any matrix time I equal to A, you see?
Yeah.
That is part of one of, this is just part of one of story. Can we just go to say how? Oh, I have to put some background first. Let's do that now. That is part of the story. How about this one? So how about the second one? How about the second example? Let's just do one more stuff. Can we just try this one? How about, let's see, if A equal to, so you just put numbers, so it's 5, 2, 5, 3, say 0, okay? So then what would be the I times I? What is I times 1? Do you want to finish that?
I is the unit matrix?
Yeah, that's I is the unit matrix.
I times A.
That's right. Yeah.
So last time we did A times I, right? We did a bit.
It's called the left. Let's call the left side. Last time we did the left side. Can you see?
Yeah.
Right side. Last time we do the right side.
Oh yeah.
Last time we timed A from the right,
Yeah.
product. So have
oh yeah, because if you have two matrices and like A times B is not the same as B times A.
Well, you will see. You will see. That's what you will do it. Why don't you do it now? Oh, well,
yeah. Okay.
Yeah. Just take this simple example to just recall what you have learned before.
Yeah. I'll just do. One times 5. So 1 times 5. That's 5. That's -1. Then it's 1 times 3. Times 3. 0 times 3. 1 times 0 is just 0, 0. It's the same.
Yep. So basically, we can also make sense. There's another conclusion we can obtain that basically I times A also equal to A. So as a whole, so in general, we can conclude in general. So if you use I, if you I times A, will equal to A times I. Will tend equal to A. So that is a very important property of what we call the unit. This is very important. And
so
go on.
So if it doesn't matter which side you multiply, it still equals A.
That's right. So it's in this case it's commutatable. It's commutative, right?
Yeah.
So you can exchange in this case only for, but this is only for the unit vector. But in general, A times B in general do not equal to B times A.
Okay.
So that is very important. Or in other
That
words,
makes sense.
in other words, A B minus B A in general not equal to 0.
Oh yeah.
But that's why. Do you know why we call the unit? Why do we call the unit vector? Unit matrix, sorry, unit matrix. Why do we call the unit?
Like unit because it's like is it sort of like multiplying by like
what do you mean the unit?
One?
Yes, that's right. So in algebra, so 1 times x will equal to x times 1 equal to x. Can you see?
Yeah.
This is just algebra. This is ordinary algebra. This is a matrix. Okay.
Yeah.
So do you know?
So unit
do you know the reason now? So that's why we call the unit matrix.
Yeah.
Of course, in algebra, we know this law that because that is due to the nature of the product, multiplication. But this is just one of the basic this is very special matrix when studying matrices.
Yeah.
Now another thing is how about the probably just use this page for a while.
Yeah.
Just good. Next one. Another is inverse. Okay, another is inverse.
Inverse. All right.
Okay. Inverse. Do you know how to define inverse?
It's like 1 over.
It's just like divide something. So inverse is something like. Can you look at the notation? How to denote the inverse matrix? So this is matrix, okay, and this is inverse. Can you see -1?
-1. Yeah.
So this one, this looks similar to that is we use take advantage of the index form. Do you remember in algebra we have say we have xn, right? Sorry, x negative n, so x negative n, right? What can we can rewrite it? We can
1
write it as
over xn.
Okay.
Yeah.
So that is why. So sometimes you can say rewrite that. Although we don't write this way, but it's just whenever you divide something, you get inverse.
Yeah.
But we don't use this notation in matrix. So can you tell me when we will encounter this inverse called inverse?
In matrices.
Yeah.
Or just
when we'll use this inverse form. Under what condition or where we discuss can we use this inverse?
Inverse.
Can we go to example? You seem to have to you don't know where one of the important application of matrices is to dealing with a simultaneous linear equation.
Oh yeah.
Okay. Can we just try one? So to 2x minus y equal to 4, right? We just make up this. So then x plus 3y will equal to 5. Okay.
Yeah.
This is a two linear equation, simultaneous linear equation, right? You can use algebra method to solve that. Okay, you can use algebra method, algebra. Then algebra method you can just substitute by substituting, right?
Yeah.
So do you remember how to do that? So you can call this equation 1, equation 2. Do you know how to remember how to solve that?
Yeah. So do you want to solve it?
Yeah. Or yeah, you can solve that.
So 2 is this is the same as x. So just sub.
Yeah, that's right. By substitution, yeah, you eliminate one. Yeah. Yeah. Okay, that's right. Then you solve x, right? So this is can we call it 3? You solve it by you just substitute, right? You into y into equation 3. Okay, we solved x. That's algebra method.
Yeah.
Now they also have the matrix method. Okay, to solve this problem, we can also have matrix method.
Matrix.
Yeah.
Yeah.
That's a very important application. That's why actually that is a main reason to invent matrix in the first place. Because when we say that when we encounter a knot of the simultaneous linear equation, right? This algebra method became a little bit inefficient.
Yeah.
Tedious. So what people say, well, why don't we it's called method. Why don't we write this a pair of the linear equation in a matrix form? So what do they do? They just rewrite this as here they use the multiplication of the two matrix. You just by pick up the coefficient. You just pick to form the what called the coefficient matrix. Can you see that?
Yeah.
Then can you prove these are equivalent to the previous, to the two equation? So that is a matrix. First, we introduce matrix to rewrite these two simultaneous linear equation. Do you know how to do? How do we justify that?
Where did the 3y come from?
Yes, it's a good question. Oh, no, it's wrong. It's just you are right. There no 3y. It's just y.
Yeah.
Y, just right. So yeah, it's just right. Do you know why we can do so?
Because so the first 2 by 2 matrix is a coefficients.
Yeah.
These are the variables.
Now, can you prove that? Can you just to prove? So can we just use your knowledge of multiplication of two matrices? Oh, by the way, this is not, so this is called the column matrix.
Yeah.
Because
the x and y one.
Yeah, you got two elements here. Now we still can use, by the way, now what can we write? So by the way, what do we get? Do we get a square matrix or a column matrix afterwards, after the multiplication?
Oh, you get, you still get a square.
Well, try it.
Yep. So it's just, since there's only, it's just 2x, right?
Yeah.
Minus y.
You don't put it two apart. They are same element. They are the same element. Can you put it here? They are same element.
Yeah. And then I'll just take mine. Then you got x.
Yeah.
Plus 3y.
Yeah. Any other product? Can you work it out?
I don't think so. Wait,
I think
2x.
So what type of matrix you obtained?
Oh.
It's column.
Oh,
right?
It's column because it's together.
So just remember this called the dimension. So this n to m is called the dimension.
Yeah.
Dimension of matrix. Okay.
Oh yeah, because it's to.
So when you time the lower dimension matrix, and the product always be reduced. Okay, reduced to the lower matrix.
Yeah.
So this is one. This is a column matrix. Okay. So then, if you compare with this, this is right hand side. This is this is left hand side, right? So how about this one? This is right hand side. This is right hand side. Are they equal? Are the two sides equal? They must equal because this is equal sign here. So therefore, they must be equal to 4.
Oh,
5.
so that's the proof of.
Yes, that is a proof.
Oh,
of course,
okay.
but of course, ultimately, you will show that you will tell people that these two, so this one, were equal to this one. You see, because they just like ordinary algebra, the same position, the same factor must be equal.
Yeah.
Similarly, this one must be equal to this one. In doing so, you just return to your equation here, you see? In doing so, you just return to your equation here. So you prove it.
Yeah. Okay.
Now this is just step 1. Step 1, let's go to step 2. In this case, can we just use same page? We don't want to jump too fast. Just clean up this thing. We know that is true. We know that is true. That's all. Yeah, we can write more information on the single page.
Yeah.
Okay. Now, can we just rewrite this as a matrix notation, right?
Yep.
So this is step 1. This is step 1. Step 2. So can we just use A times X vector? So we can treat this as vectors, okay? As vectors.
The column.
Yeah, column. Yeah.
Yeah.
And another side is constant. Can you see?
Oh, vectors because it's like it's on the plane, right?
That's right.
Yeah.
So it's just matrix, or you can call it matrix, or you can call it column. You still can call it column matrix, right?
Yeah.
So what is X here? So in this donation, in this notation, A, so this we just continue here. So we just continue here. So A will equal to 2, 1, -1, 3. That's called the coefficient matrix, right? And the X matrix will equal to just X and Y. See?
Yeah.
And of course, the C is C. What is C? C will just a coefficient. This is a left-hand side. This is a right-hand side constant. It's called a constant matrix. So if you look at this, something very important you have to. What does that mean? So this come to our knowledge of the product of matrix. I think we talk about this before. So what does this mean? You got 2 vectors. You got 2 vectors, right?
Yeah.
Just talk about the implication of the graphical implication. So we got 2 matrix, 2 vectors, 2 vector. You see, we just started vector last week, right?
Yeah.
I've got 2 vectors here. So basically, what does it mean is that you have this coordinate. Can we just do this coordinate here? So basically, we know the C. We know the C vector. Can we just use arrow to represent the vector? So we know that there's a vectors. There's vectors. This is C. Okay. We know there's C here. But what we don't know is a vector. Oh, it's like a position vector. Okay.
The X vector, right?
The X vector. What we don't know is this vector. Can you see?
Yeah.
So that is how sometimes you have to combine your algebra with is a graphical interpretation, right?
So basically, it's like you're multiplying a vector.
That's right. So this is our X vectors. This to be determined. After all, if you just look at the position, it's just X and Y. So X, Y are unknown. X, Y are unknown, right?
Yeah.
So this is our C. So in this C, okay. Of course, this coordinate is X and Y. This is origin. So basically, what does it mean when you time the metric? When you time the vector by a matrix, I mean, times a square matrix.
Yeah.
What does it mean? They just transform this vector.
Transform a vector
into the new vector.
New vector. Yeah.
This operation, this transformation is just called A. Can you see?
Yeah.
Makes sense? So
okay.
A is kind of transformation. So A is transformation vector, right?
Yeah. Oh, is that the name? Transformation vector?
It is transformation. You can call you can call this the reason. So any vectors, you have any vector, if you time the matrix, they will either change direction or their magnitude or both. In this case, both, right?
Both.
In the special case, you can rotate vector. Okay.
Oh, really? Okay.
By the way, can we just return to the unit vector? If you just use this form, so if you use the unit vector times x, what we obtain?
Unit vector.
Yes, I is unit. Unit matrix. I is unit vector. If you use if you multiply a vector by a unit matrix, what will you obtain?
Let me think about this.
Well, you can
get the same thing, right?
Yeah, you get the same thing. You can consider that vector as a special case of column matrix.
Okay.
So in other words, if you just time if you time x, nothing would change. Nothing would change. Oh, hang on. We have to this is another thing.
Yeah.
We have to explain this one properly. It is something conceptual where the concept must be clear. Let me just rewrite this a little bit. I cannot call this a transformation. This is opposite transformation. Now in our equation, when in this equation, so So in this equation, right, what happened is that we just said we got the x, if we got the x vector, if multiply the coefficient matrix, then we can obtain the new vector. But in this question, in other words, if in this case we can draw that diagram. So in this case, you can see that this should be because that the transformation go other way around. So this is A, okay? Can you see?
Yeah.
If we knew the position vector x, right? If you multiply A matrix, you
multiply x to get to C.
You get to C. But the question in our question, when we solve the simultaneous linear equation, we know this vector. We know this what is 4, 5, right?
4, 5.
We know C. Yeah. C is given.
Yeah.
What is unknown is x, y.
X and y.
In other words, we need to find the opposite or inverse transformation.
Yeah.
Can you see? So this inverse transformation is called A inverse. Can you see?
Oh, wait a minute. So basically,
yeah.
Okay. So when you have the vector x, you transform it using A.
Yes.
So then you want to find the coordinates of the original vector, you need to use the inverse.
That's right.
Oh.
So
okay.
If I just write everything's here. So because see, if you use another method, so that is original matrix equation. See, this is matrix equation. Okay, not the ordinary algebra, is matrix equation. See, so why don't we multiply from A inverse from the right hand side? From there.
C times A inverse will give you
Can
x.
we just Can we just time A inverse, right?
On x. Both sides.
Yeah, on both sides. So we got A inverse and times C. Yeah. Do you agree?
Okay. So so if you times on both sides, you have to
inverse,
pick
with inverse.
And if it's either left side or right side, right?
This time from the left hand side. Yeah, this
Yeah.
we from left hand side. Multiply this way. Multiply this way.
Yeah.
Now we get this very interesting phenomena here. In algebra, do you remember if you in algebra x times x minus 1, what do you get?
X to the power of 0, which is 1.
So x divided by x, right, equal to 1.
1.
Okay.
Yeah.
So similarly, in matrix, what would you expect?
I'd expect 1.
What would you expect to this product? What matrix? What type? Can you guess what the metric? What type of matrix we will obtain if we multiply the matrix and its inverse?
What type of matrix?
Yeah.
Unit?
Yes. Go on.
Oh, what?
Yes,
For
that's
real?
right. Yes, it's just it's called an energy. It is called a unit. Can you see? So this is algebra and is an energy. So you have to this. Of course, this is algebra. Okay, this is algebra.
Oh, because you get a unit.
You get a unit. You get a unit. So as I say, although we don't write this way in textbook, but you can, as a learner, you can just rewrite. Say, oh, a inverse a can be rewritten as you say 1 over a times a. So the a cancelled equal to 1. Can you see?
Yeah.
This is of course this is not strictly correct. Okay, but you can make it sense. If you really want to know why this product gives the unit, then you just use algebra and energy analog.
Yeah.
You compare with algebra operation.
Yeah. So unit vector, it literally represents a unit. That's why, right? Because
they say the product of matrix and its inverse and its own inverse matrix equal to unit.
Yeah. Equals unit.
Can you do this? But how about this one? How about let's answer this question. How about this one? We at the beginning, in this case, we time it from the right hand side. Now, how about this one? How about a multiply inverse from behind or from the right hand? What would you expect to obtain?
I'd expect the same thing.
Same thing, yeah.
Yeah.
So it's a unit, right? It's a unit.
Yeah.
It's true. It is true.
Yeah. Oh, okay.
Now, if so, what we can say? If so, what we can obtain from this one? So from this one, so what we can conclude? We come all the way to solve, because our objective, don't forget our objective here
is to solve x and y.
Solve the pair of linear equations, right?
Yeah.
In other words, we need to find what is x and what is y.
Yeah.
So now from here, it's very important, the breakthrough is that to say, we do say this is formula for x will equal to a inverse times c, okay?
Yeah.
That is a matrix method to solve the simultaneous equation.
Oh, all right, that makes sense.
Do you remember that? So the whole thing, the objective became how to find the inverse of the coefficient matrix.
Yeah.
Once we know that, then we should be able to find the solution for x and y.
Yeah. So to obtain the inverse.
Yeah, that's another issue. How to obtain the inverse? That's another issue. Yes.
Yeah.
How to obtain the inverse? Yeah, that's a second. That would be next question.
Oh, so the benefit of matrix when you're solving it is, if you know the inverse, then you can solve directly for x and y, right? Like with
that's right. But of course, it costs time when you're actually trying to find that inverse matrix, right?
Yeah.
But in this way, you don't have to go back to that the algebra method by eliminating y or eliminating x, right?
Yeah.
By substitution. So this is different method. This is the benefit of this matrix method to solve simultaneous linear equations will show up if you are trying to solve many simultaneous equations together.
Yeah.
So let's go to the next question. How to find the inverse, right?
Is it?
Do you remember? Do you remember the form? There is a formula here.
I think so. It's like.
Can we just start from 2 by 2 because 3 by 3 is a little bit tedious, right? You have. Oh, by the way, if you forgot everything, you have to start from the 2 by 2, right?
Yeah.
So our question is how now the next topic is how to find the inverse. There are two ways to. One is actually prove that to derive the formula from the algebra method.
Does it? I remember it's something over the determinant.
Determinant, yeah. You have to, yeah.
Right?
How to, yeah. You have no other things. So how to obtain, how to find, inverse matrix. Well, there's a formula here. You can first use a formula, but basically, if you have time, we have to go to the algebra method to prove that, right? So can we just say this is so given? So this is given. A is a matrix. Can we say that? Can we just go to A, B, C, D?
A, B, C, D?
Yeah, that's easy to write.
Yeah.
So then the formula. So the formula for the inverse. Inverse for the inverse. A inverse. This just that's just for people who in those days. You know what? In older days, in ancient time, mathematicians have to spend some time to provide ordinary people some method. It's called algorithm, in order to apply mathematics. Okay. Of course, nowadays you just open any calculator or even online matrix calculator. You can.
And I'll do it for you.
So therefore, I just read the formula here, okay, because otherwise it's determinant. So basically got this determinant here, determinant A, and then you have the new matrix here is called this matrix called the multiply. So you have to basically remember you have the exchange A and D, right? You can B and A. I think that's the way to go. And then you have multiply this negative sign here.
Negative numbers, negative, yeah.
Is that correct?
Oh, yeah.
That's correct. You have double check that. I will double check that for you.
Because that looks fine.
No, well, make sure it's correct. Okay, make sure.
Yeah.
So that is how, if you go back to a textbook, you should be able to find that formula as well to see which.
Yeah. Oh, okay.
If you go to matrices.
I think I got it here.
Yep.
DB
inverse
minus
A and B. Yeah, that's correct. That's correct.
Determinant.
Yeah.
The determinant's AD minus BC.
Yeah. So how do you remember how to find the determinant A?
Yeah, it's AD minus BC.
Yeah.
Right.
That is just this determinant notation here. That is A, B, C, D, right?
Yeah.
So you just again, as I said, matrix is just the algebra, the method. So what you do is that you follow this one. So if you use the product here, you got a positive. If you pick up another side, you keep this one, you get a negative. So basically, that's how I remember that when I learned in high school. So you get a positive here, you get negative here. So otherwise, you get two terms. So one is A times D minus, can you see, B times C.
Yeah.
This is formula.
Yeah.
Now, can you go back to pick up that example? What is our matrix? Do you remember? Do you remember the matrix A we pick up is 1? Is 1, 3? Is 1,
2,
3?
I'm thinks.
Let's just go back.
I think it was 2.
2, negative 1. 2, negative
Yeah.
1. 1, 3.
And 1, 3.
Yeah. It's 2, negative 1. 2, negative 1. And 1, 3, right?
Yep.
Do you want to try how to find the inverse A?
Inverse?
Yeah,
Yep.
inverse A in this particular example. Just use this formula.
So it'll be
We call it D is for determinant. D E T for determinant.
yeah. So it'll be 3, 2, 1, negative 1 over.
You have to find the determinant here.
Yep. Plus 1, which is.
Yep.
Is that it?
Yeah.
That look.
Mm-hmm.
So that's.
Can you just multiply the factor? Can you multiply 7? You just multiply in order to get a square matrix. You got a 3 over 7.
Oh yeah.
1 over 7. Can you see that? 1 over 7.
Oh, okay.
2 over
Yeah.
7. So that is
So you divide every part
every element. You divide every element by 7.
By 7. Oh, okay.
So that's it. Easy. So basically, what is x? So what is x? So therefore, what we can so the x. What is x? X is x and y. X and y were equal to A inverse times C vectors, right?
Yep. And
we got this here. Yeah, you can do it. So what is can we just copy this inverse here?
3, 7.
Yeah.
Negative 1, 7.
Mm-hmm.
1, 7. 7 by, and it was 4 and, oh, sorry.
4 and 5 or something?
Yeah, it was just 4 and 5. Yeah.
Okay, double check. Yeah, 4 and 5. Yeah, 4 and 5. Yeah.
Oh, yeah.
Okay, can you finish this multiplication of 2 matrix?
Yep. So it'll be 7 and
that's quick. Yeah, that's quick.
And 15.
Yeah. So in this way, you got x and y directly. You can see what is x and y.
Oh yeah. So x is equal to then 15 over 7.
Yeah.
Oh, okay. So it's if it's a higher order matrix multiplied by lower order, it's the lower one.
No dimension. No
dimension.
Dimension. Yeah. You got lower. You pick up the dimension. The product will be no dimension.
Yeah. Actually, I think I multiplied it. Oh no, I didn't multiply correctly.
Correctly, yeah.
I think I missed something. Wait, no, I did that wrong. I'm pretty
there's
sure.
A negative sign. There's some negative sign here.
No, it's meant to be. So it's meant to be.
This is negative. So this is negative. Can you see?
Is it?
Yeah, because this. Can you see? This is negative sign here. You missed out. See this negative sign.
Yeah, I know. I think I'm pretty sure I expanded it. Not expanded, but I did this part wrong. Like in here, I think. Oh, whoops. think I did this part wrong.
So basically, you said 3/7 multiply 4, right?
Yep. So that's 12/7 plus, would it be 1/7 multiplied by 5?
Yes, that's right. 5
Yeah.
over 5/7, yes.
And then this is
Negative, because negative.
yeah, that's another problem. Yeah. Plus 10/, yeah, this seems correct. Yeah.
Yeah.
I just so it'd be, because I was thinking of what I got for the substitution, the algebra, and it's a bit different. So I was just double checking.
I hope today's your review will help you to pick up what we have learned before.
Yeah. Okay. So I just had to remember the multiplication. It's column row.
Yeah, well, it is relatively easier if you times a column matrix.
Yeah.
So I think let's just give you a summary to here briefly. So basically, when you're dealing with metrics, you will consider their graphical meaning. It will be helpful if you know some graphical meaning. So if you multiply, so that will be a kind of extension of what we have learned before. Or basically, can we just use two more example? Can we just use another example? So if you have, for example, you have, let's give you example here. So if you just put the matrix, a vector here, so this vector can we call, or this is a column, it's called a column matrix. If this column matrix, it is original here, so this is an original matrix.
Yeah.
Yeah, just take for example. Can we call this is matrix? Can we call it coordinate? Can we call this point is P?
P?
Right? Yeah. Can we call this 4 and 5 and 3? 5 and 3, right?
Yep.
Now, if you just, I'm asking. So if you just, of course, we got this called C vector. So that's a given. So it's got another example, it's a given example.
Yeah.
Given, say C is a vector, let's say right here the 5 and 3, right?
Yeah.
Now then we just transformation, I give you some importance. Can we just, if you get a transformation, so this transformation, so it's called a of course, every matrix here can be considered as a transformation, okay?
Yeah.
Transformation matrix. In other words, every transformation in mathematics, we can be represented by appropriate matrix. Okay.
Okay.
I just use R here. I give you the simple one. This just would be 0, 0, 0, 0, and 1, -1. Okay. The question: what would be the new vector? So question. So R time after transformation, what we obtained?
So this is a bit different. All right.
Well, it's the same question. So we multiply a vector by a square matrix, right?
So
you don't have to call it the transformation. You just call the matrix. Okay.
So in the order, it's RC.
Yeah, R times C, because it's operate. You apply this operator on the metric on the vector C.
So it goes on the left, from the left.
Before you go to detail, can you tell me what type of the result we would obtain?
So R looks like the unit matrix, So,
No,
but it's
it's
got
not. It's not. Unit vector.
Yeah.
You don't forget that just because you see 0, 0 doesn't mean. So unit vector is that. Can you see it's different? 1, 1.
Yeah, it's
yeah.
got a this one. It looks like it, but it's not.
It's not.
That's
It's not. It's not. So,
yeah.
so certainly RE is not equal. Not the same thing. No.
So I'm probably thinking some sort of like it'll become negative or like become.
No. Shall we? In other words, shall we obtain another vector? Shall we obtain another vector?
Yeah. Yeah.
Okay. Which direction? You don't know. Doesn't matter. Doesn't matter. We will obtain another vector for sure.
Yeah.
Right?
I think we're getting a different one. Yeah.
Okay. Go on. Can you try that?
So 0, 0. And then negative 3.
Yep, that's right.
Oh.
Hang on, the negative 3, right? Be careful. It's a negative 3.
Yeah.
Negative 3. Okay, that is one. Negative 3.
Yeah.
So can you draw this diagram here? Can you just roughly draw where this is a metric, where this vector point? How to draw, how to represent this matrix here? So this is roughly, this is 5. Okay, this is 5. And
It's like a
3, yeah, this is 3.
So this is. Oh wait, no, that's wrong. That's wrong. It's
negative 3.
Negative 3.
So
yeah.
somewhere here. So somewhere here. Can you see? Just negative 3. Somewhere here, right? Negative 3 here.
Oh yeah. Oh, that's
5 here. Can put a 5 here, right? There's 3 and 5. Yeah, roughly.
That's kind of weird. Oh,
it's
yeah.
not weird. It's very interesting. I can tell what.
Yeah.
You can actually prove that this angle is a right angle.
Oh, really?
Yes, it's a right angle.
Oh.
So that's why when you actually these are, if you write this notation, they call the half pi here. That's how we denote this transformation. 0, 0, 1, negative 1, which means this half pi here means that you actually rotate.
Like,
you actually rotate this by 90 degrees.
So that forms. Does that mean the triangles are similar? Like, you know how you can.
Oh, the triangle are similar. Yeah, you can spend some time to work out that. So basically, these triangles are similar. So these triangles are similar.
Yeah. Oh, that's pretty cool. That's pretty
so
cool.
This triangle and this triangle are similar. Yeah.
Yeah.
Not similar. So congruent.
Congruent. Yeah.
Yeah. Congruent.
So it's like it's like you have an angle. Add pi over 2.
Yeah, it's just like, matrix just play the role of the rotation transformation, you see.
Oh, so that's how you rotate.
Yeah.
A vector.
Yeah, I hope you can remember this special matrix, and we can discuss next time. Oh, time's over. Okay. See you next time. Yeah. Tomorrow.
All right. I'll see you tomorrow.
Goodbye.
All right.
Bye.
Goodbye.